So the orbital tuning itself, you can do with anything you want, really. You can use the eccentricity, you can use the obliquity, you can use the precession, or even the insolation at 65 degrees north, which are, very common target for this type of practice. Now, which one you choose exactly depends on how you understand the link between your record and the forcing mechanism. In other words, the orbital parameters. So it's really important to have a good understanding of this. And then the principle is fairly simple. Let's take as an example that we have eccentricity as our forcing mechanism. So we have a calculated eccentricity with calculated ages. So we know exactly when these eccentricity cycles were. You can see the 100,000 year, 400,000 years. And then we have our record. In this case, we'll use oxygen isotopes. So that's the red curve. In red, the red numbers, we have the interglacial, so 1, 5, 7, 9, the warmer period. In blue, we have the glacial period. And if we know, for instance, that our interglacial in this particular area correspond to eccentricity peaks, we can tie these things together, and so we obtain a calculated solution or orbital solution for our record. Now, our solution is only as good as our independent dating. That's why it's so important to have good independent dating so that we can essentially do that tie properly. So how does that apply actually to deep water sediments? How can we apply orbital tuning to deep water sediments, to cores that would be recovered by a ship like the Chikyu, for instance? Let's look at one example, and I'll bring you to the Mediterranean, where we have a beautiful record of sapropel deposits. So in the Mediterranean, several crews, of course, took place to recover sediments. Some of them ODP cruises, but not just ODP cruises, multiple cruises from different nations, because the Mediterranean is really the vestige of the Tethys Ocean, and it's a semi-enclosed basin, so it records and amplifies climate signals more than, say, the Atlantic Ocean or the Pacific Ocean. So a really interesting place to study. And if you looked at a cross-section of the current Mediterranean, so that would be that yellow line, and you specifically looked at salinity, what you would see is that salinity changes from west to east in the Mediterranean. So in the west, over the Gibraltar Strait, we have the income of less saline surface water from the Atlantic Ocean. But as it travels eastward, of course, the aridity in the Mediterranean region is very high. So you have a lot of evaporation taking place, which means that you get towards Turkey and the eastern Mediterranean basin much more saline, warmer waters that then tend to sink into the Mediterranean basin and eventually flow out back into the Atlantic at mid-glacial depths as a saline Mediterranean water outflow. This circulation has tremendous implication because this circulation also means that you bring oxygen to the deep basin, so you have a well-oxygenated deep Mediterranean basin in the present day. But we know that this was not always the case in the past, and in fact, if you look at the Mediterranean during what is known as sapropel S1 and S2, you see that we go from oxygenated condition to less oxygenated condition where we can deposit the sapropel layers. Sapropel are sediments rich in organic matter. So this is for S1, but the same applies also for sapropel S5. And if you look at these sapropels, they're absolutely interesting in terms of their sedimentary nature because they are dark sediments, very laminated, again, all of this indicating lack of oxygen and the potential to preserve those laminae. And you can see them in cores, but you can also see them at the outcrop. You have an alternation of carbonate-rich deposits where you have more oxygen and clay-rich deposits with more organic matter in between those carbonate deposits. So let's have a look at how we can use sapropel, or how sapropel have been used for orbital tuning. And maybe one of the best example is using the record of Sicily. So the base of the Zanclean stage is defined at Heraclea Minoa in Sicily. And this is work done by Van Covering and his team and published in 2000. So you have here the location of Heraclea Minoa. You can see Sicily and Calabria. And the point is, at this particular location, without going into too much detail, we can see an alternance of carbonate-rich deposits and deposits that are less rich in carbonates but much more rich in organic matter. In other words, the sapropels. And you can see when you look at this record that this is a very frequent alternation between sapropel condition, where things are not oxygenated, and non-sapropel condition when the basin is oxygenated the same way as it is today in the Mediterranean. And so we can use that alternation because we know from previous studies that sapropel are driven by precession and insolation. We can tie each one of the sapropel layer to peaks in precession, and so obtain a very precisely dated record here thanks to the alternation of sapropel in this deep sedimentary basin in the deep Mediterranean, where we have a continuous record of sedimentation, unlike what you would expect if you were looking at a shallow water deposit. And so this is how the orbital tuning technique can be used to do very precise dating and very accurate chronostratigraphy. And it's really used a lot in modern stratigraphy to determine the exact age of the base of different stages, as we'll see in our last lecture. And in this case, in Heraclea Minoa, I was showing you the base of the Zanclean stage. So for the next lecture, I will still be on the Chikyu. I just love that ship. I won't leave it so soon. But this time we'll talk about something different. We'll talk about stratigraphy post-mortem, or what happened to sediment after deposition. In other words, diagenesis.